My name is Romeo Bruni, and today we're going to discuss accretion disks. Accretion disks are the most important sculptor in the universe. More important than Rodin, more important than Donatello, more important than Michelangelo or Henry Moore. Accretion disks are responsible for some of the most beautiful things in the universe, like spiral galaxies and the rings of Saturn are accretion disks. They're responsible for the most powerful engines in the universe, quasars. They're responsible for evidence of black holes, the most important evidence of black holes we have, in the form of X-ray binaries. And they're responsible for the most important standard candle and one of the brightest events possible in nature, and that's a type 1a supernova, where matter accretes into a white dwarf, and we'll discuss that. And then the type 1a supernova explodes. And of course, accretion disks are responsible for protoplanetary disks, which go on to form planetary systems and solar systems. And without them, we probably wouldn't have life. And in fact, accretion disks are also responsible for how water streams off a wet spinning tennis ball, also a type of accretion disk. Let's go through these in order and discuss accretion disks. Accretion disks take place in nature. They're ubiquitous whenever you have a combination of a central gravitational force and angular momentum. When you have angular momentum rotating around something central that's very heavy, the complex physics involved cause the matter to accrete down into a flat disk, continuously spinning around. These flat disks are ubiquitous in nature, and you see them. Oops, sorry about that. The flat disk. That is the spiral galaxy, the flat disks that are the rings of Saturn, the flat disk that forms the quasar, all from accretion disks. Let's go through them one by one. First of all, spiral galaxies. Spiral galaxies are an unusual form of accretion disk in that almost all accretion disks are from a central, very dense star or something heavy, and then matter circulating around it, with the mass at the center being the accretor and the gravitational force. With spiral galaxies, although all spiral galaxies have a supermassive black hole at the center, the black hole at the center is not nearly big enough to accrete the whole galaxy. It's a very tiny percentage of the weight of the galaxy, so it will not accrete a galaxy. In spiral galaxies, the main gravitational force or matter that's providing the gravity is dark matter. And what happens is, out of the Big Bang, you have clouds emerge, and the clouds have only three things: hydrogen, helium, and dark matter. Initially, the hydrogen, the helium, and dark matter are all spinning coherently. All spinning coherently. The dark matter is 85% of the mass. The dark matter provides the gravitational well that accretes hydrogen and helium down into a flat disk, compressing the hydrogen and helium and probably helping to initiate star formation. And so spiral galaxies are accretion disks. The accretor is not the central massive black hole. The accretor is actually the spherically, coherently spinning dark matter, which over time will accrete the heavier matter, the hydrogen and helium, down. Hydrogen and helium, of course, combine and form clouds, which condense and get denser and denser, and eventually form stars and galaxies. All galaxies in the universe began as spiral galaxies. All the other types of galaxies, the elliptical galaxies and the unusual types mergers of spiral galaxies. So spiral galaxies, very beautiful. Thanks to accretion disks, we have them. Next, let's discuss cataclysmic variables. In a cataclysmic variable, you have a small star, which is a white dwarf. Now, a white dwarf is what results from a smaller size star at the end of its life. When stars die, depending on their size, they form various things. If they're very small, when they die, they'll form a brown dwarf. If they're a bit bigger, like our sun, when they die, they'll contract and get very dense and form a white dwarf. If they're bigger still, when they die, they'll form a neutron star. The very biggest of the stars, when they die, will form huge black holes. So white dwarfs are one of the types of remnant stars. Now, what happens is that, well, first of all, it's important to know that at least half, perhaps more of the stars in the universe are in binary systems. So when you look up at the sky, half of those stars you're looking at that look like one point are actually two stars rotating around each other, and that's very important. So what happens is that you have a white dwarf, that's a previous star that has already died, and the remnant is very hot and dense and contains a lot of carbon and nitrogen and things, and it's in a binary system with another star, which is also in the process of dying, and before stars die, even before the white dwarf stage, they form giants, either red giants or red supergiants. So if another star that's in a binary system with a white dwarf increases its size, then matter will start to funnel from the bigger star to the white dwarf. So we have matter funneling from that bigger star to the white dwarf. And that will gradually increase the size of the white dwarf. That's visualized here. Here we have a red giant, and the matter is slowly being drawn towards the white dwarf. And of course, it forms an accretion disk around the white dwarf. And because matter is funneling in to the white dwarf, it's slowly increasing in mass. And once it reaches a certain critical mass, and that's 1.4 solar masses, that's called the Chandrasekhar limit, it cannot support itself anymore. It's become too heavy, and gravity takes over again. And it initiates a series of events that essentially a nuclear cataclysmic chain reaction takes place, so that all the matter in that white dwarf compresses and then detonates, so that all the matter is converted into pure energy. It's the only type of supernova where the complete totality of the matter is converted into pure energy. And that forms, of course, a type 1a supernova. Now, the importance of this cannot be underestimated, because the star will always explode at exactly 1.4 solar masses, the Chandrasekhar limit. We have a set amount of matter being converted into energy, so we know exactly how much energy has been produced. Therefore, if we see a type 1a supernova in some far distant galaxy, we know exactly how much energy was produced by that type 1a supernova, and we can figure out it's a 1a supernova by analyzing the light spectrum, and it'll have a very distinctive light spectrum and pattern over a few days as it falls off, so we know it's a 1a. We know exactly how much light was emitted, and by comparing how much light was emitted to how much light we receive on Earth, the standard candle versus how much we receive, there's a ratio there that will tell us exactly how far away that explosion was. And determining distances to stars is probably the most important and most difficult thing in astronomy. So So having a standard candle like this, which is visible deep into space, is incredibly valuable. So it cannot be understated, the importance of type 1a supernovas. Again, because of accretion disks. Otherwise, we would not have them. Another type of very important accretion disk that's very similar to that is X-ray binaries. Now, X-ray binaries are actually a very similar system to what we discussed with the cataclysmic variables. And the difference is that you have an accretor, but that accretor is no longer a white dwarf. That accretor is either a neutron star, which is a collapsed star, which is incredibly dense. It's like if the sun were to collapse into a neutron star, it would be probably the size of a small city, something like that, incredibly dense, or a black hole. So either a neutron star or a black hole. Again, it's in a binary system where the other star has become a red giant usually, or a super red giant. Those are phases that stars go through in their dying process. They actually swell up. In fact, the sun in 2-3 billion years will start to swell up and become a red giant and make it very hot on the Earth. So because we have a bigger star, much less dense, again, we have matter funneling in towards the black hole or the neutron star and forming an accretion disk around the black hole or the neutron star. Now, what happens when you do that, and this is very important, you have the accretion disk around the black hole and the neutron star, and as it funnels in, it gets the stuff funneling in gets hotter and hotter and hotter. So at the outside edges, it's not too hot, but hot enough, and you'll start to get infrared light coming from the outer edges. As you go closer and closer, it's spinning faster and faster, and therefore it gets hotter and hotter. The hotter it gets, the higher energy radiation it's going to emit, so that near the center or near the Schwarzschild radius, you're going to get the matter circulating so fast that it's releasing X-ray photons or light, and that's why they're called X-ray binaries. In addition, because the matter swirling in tends to be charged, it creates an incredible magnetic field, which leads to jets shooting out from the black hole or the neutron star in the direction parallel to the spin axes. So if the thing is spinning like this, the accretion disk forms like this, but the jets will go up in either direction. The jets are electrons and other charged particles that are shooting out at incredibly fast speeds. We call those relativistic speeds. When speeds get near the speed of light, it's called relativistic speeds. And when charged matter is traveling at relativistic speeds, and it tends to be spinning because of the magnetic effect, when you have charged matter spinning and being drawn in circles, it emits radiation also. It's called synchrotron radiation. So the jets too will be emitting incredible radiation into space. And if we happen to be on the Earth, for example, in the path of one of these jets, we're going to notice it. That we call those radio galaxies. But really, they're just another type of X-ray binary. So again, and it's interesting that black holes, of course, are black. They don't emit any light. But because black holes, like all other stars, tend to develop accretion disks, and the accretion disk is the matter swirling in the flat plane, and the accretion gets very hot, it emits radiation, i.e. light. And so black holes are visible because of the accretion disks that are around them. Perhaps you've seen an accretion disk of the black hole at the center of our Milky Way galaxy. It's called Sagittarius A star. It's only recently that we've been able to peer through the cloud and dust at the center of the galaxy and get pictures of it. And in fact, it's an incredible accretion disk around our Sagittarius A star. So that type of accretion disk is also very important. Now, a very similar type of accretion disk is what develops in what we call a quasar. Now, a quasar is actually very, very similar to an X-ray binary. The difference is that the central massive, the black hole at the center of a quasar is a supermassive black hole at the center of a galaxy. So it's not just your ordinary black hole, it's the supermassive black hole at the center of the spiral galaxy. Every spiral galaxy has a supermassive black hole at the center. The average weight of the supermassive black hole is approximately 3 to 5 million solar suns weight. So they're incredibly huge. And they have a similar, and unlike X-ray binaries here, so here in this case, we have a supermassive black hole at the center of a galaxy. And if it's a young galaxy, you have a lot of stuff around it. But the supermassive black hole forms an accretion disk around it, just because there's so much stuff there. And not because you have another star in a binary system feeding it, but you have a supermassive black hole and you have an accretion disk, which is incredibly huge. They're essentially even larger than solar systems. Now, this accretion disk, just like X-ray binaries, are going to have jets popping out of them, like this. Well, there's like a type of a quasar, where you have the accretion disk, and it's all just stuff from the galaxy accreting to it, no binary. And of course, you have the huge jets coming out of this accretion disk too. So a quasar is the accretion disk of a supermassive black hole at the center of galaxies. Now, every spiral galaxy has a supermassive black hole, but very few galaxies are actually quasars. And that's because with time, the massive black hole has already eaten, if you will, most of the matter. And so very little matter is funneling in, very little energy is produced in the accretion disk. Just like Sagittarius A star, the galaxy at the center of the Milky Way is not a quasar because it is not eating up a lot of material, therefore not funneling out energy. But younger galaxies, like the galaxies we're seeing with the James Webb, or galaxies when we peer far into space, which is back into time, where galaxies, if you will, are a lot messier and there's a lot more stuff around. Those are called active galactic nuclei, or that means that they're active galaxies in that a lot of matter is being funneled in via the accretion disk and generating huge amounts of energy. As we described, on the very outside, the matter is moving slowly and it's hot, but not that hot, so it's generating lower energy photons. As you get closer and closer, it gets hotter and hotter, and the hotter it is, the higher energy photons it will emit. And because basically we have the full spectrum, from not too hot to very hot in the center, that releases the full spectrum of light. And when something is releasing the full spectrum of light, that's called black body radiation. So quasars are going to emit black body radiation. In other words, light in all the different wavelengths from very low energy to very high energy. And of course, quasars are going to have very, very powerful jets, which will beam out at the poles. And if those jets happen to be oriented so that they're facing the Earth, we perceive them as incredibly powerful light coming into us. So quasars also, and quasars, the amount of energy and light produced by a quasar, even though it's only the size of a solar system, it's so powerful, the amount of light from a quasar will outstrip and emit more light than the whole galaxy, which is hundreds of millions of times larger and contains billions of stars, yet the quasar at the center around the supermassive black hole, which is really the size of just a solar system, gets so hot and with the jets is producing way more light than the whole galaxy. That's how powerful quasars. Now, it's already apparent how important accretion disks are. They are the genesis of spiral galaxies, the genesis of type 1a supernovas, which are the most important standard candle probably in astronomy. They give us X-ray binaries, and X-ray binaries are important to even detect black holes, because to detect black holes, because they're black, you can only see light from the accretion disk, and because they're in a binary system, you can see the neighbor star, so you can calculate how much the black star weighs based on just the gravity and the rotation of the two around each other. We've shown how accretion disks are key for quasars, which are the most powerful continuous engines in the universe. And finally, and perhaps most importantly, protoplanetary disks are accretion disks. The solar system is an accretion disk. It's been flattened out, and just like all other accretion disks. And that's why all the planets, when you see them go through the sky, they're always on the same plane. It's called the ecliptic plane, because the solar system and all solar systems form in a planetary disk. And you can see planets forming. So accretion disks are responsible for protoplanetary disks, which in turn are responsible for planets. And of course, if we didn't have planets, we wouldn't have life. So accretion disks are not just the most beautiful, not just the most powerful, not just the most important standard candle, but probably in fact also responsible for life, in that they're instrumental for the production of planets. Now, just as an aside and a final point, that is also a type of accretion disk. And that is a wet tennis ball. A wet tennis ball spinning. And what happens there is it's the same thing. The spinning is the angular momentum. And rather than the accretor being gravity, in this case the accretor is surface tension. The water is trying to hang on to the tennis ball because of surface tension. Of course, surface tension is a manifestation of the electromagnetic force, which is one of the other great attractive forces in nature. So it's also a type of accretion disk where the accretor and force is not gravity, but it's the electromagnetic force via surface tension. So to summarize, accretion disks are the great sculptor of the universe. Without them, we wouldn't have spiral galaxies. Without them, we wouldn't have X-ray binaries and evidence of black holes. We wouldn't be able to see black holes. We wouldn't have the strongest, most bright light in the universe, a quasar, which is important because it allows us to peer deep into space and to see billions of years into the past. And of course, life. We wouldn't have life because we wouldn't have planets. accretion disks are key.